Okay, so uh, today we are going to look at a framework for consistency algorithm. This is joint work with Peter Keeney, and this is for the conference FSCTCS 2020. Of course, this is recorded online, and since I found it very strange to be talking to the monitor, I also invited my co-author as a only audience for this talk, and he will probably represent those who are viewing this presentation much later. So let's go into the talk. The talk is about consistency algorithms for certain kind of memory models. Uh, I will define what is meant by consistency and what is meant by memory model. But before we start, okay, I roughly go into what are the parts of this talk. So we talk about concurrency, what are concurrent programs, what are relaxed memories, and what is the semantics of running a concurrent program over this relaxed memory. We talk about notions of correctness for these concurrent programs with respect to relaxed memory, and then we will see to how to get a optimal algorithm or a framework for reasoning about correctness of such a notion of a version of correctness for this relaxed memory concurrent relaxed memory programs. So what are concurrent programs? These are finite threads interacting through shared variables. So you have a set of threads, you can say P1 to Pn, and you have a set of variables X, Y, Z. And these threads can read or write to this shared memory. They can write from a finite set of data. Now, the memory model actually determines the way the thread behaves. So the memory model can say, okay, certain reorderings in your thread can happen. So we will come to this in a bit more detail in sequel. So the memory model determines how the thread behaves. And a valid execution requires that the axioms of the memory models are satisfied and that all the reads have a corresponding write from which a real write from which it has read the value. So during this talk, we merge these 2 points and sometimes call both these points as consistency check. So well-known memory model is called sequential consistency. This is what we imagine a computer to behave like. So the sequential consistency does not allow any reordering of instructions within a program. So it is like each of the operations, the read or write operations that you perform are atomic. The moment you read a value, it is read from the main memory, and moment you write a value, it is immediately updated to the main memory. All these threads execute in sequence. So this means that there are no reordering of the instructions of the thread. So valid execution in this semantics is whether each reads of the program have read a write value, that is a committed value. So the consistency here means that each of the reads are satisfied. So this essentially gives us a valid execution. Let us understand this with the help of an example. So what does sequential consistency mean? So when you write y equal to 1, y is updated into the main memory. And when you read a x, the value for x is read from the main memory. For example, this is a mutual exclusion protocol, and it says that the critical section should not be reached by both the programs. This guards against whether critical section is mutually exclusive. So the first thread executes, it writes a 0. Now the second thread starts executing. He now writes a 1 to the main memory, checks whether y is 0, enters his critical section, and updates x to 0. So in this particular program, in this mutual exclusion program, two threads cannot simultaneously enter the critical section. This is because we have assumed sequential consistency, but this need not be the case for other kind of memory models. So here in this case, you can think of a valid execution as the shuffle of threads such that the reads are consistent. Or the other way of thinking of it is there a total order on the set of all instructions of all the threads such that the program order is satisfied? I mean, that is each thread, the program order is maintained and all the reads are consistent. That is that the reads read a value that has been committed before. So, I mean, this sequential consistency is it is very close to intuitive behavior in the sense that it allows for each operations of your program to be committed immediately. The reads and writes are committed immediately. However, this can be very slow because the write operations are quite costly in some sense. So the writes are very slow in some sense. So the whole program can execute in a very slow manner. So there usually the processors that we have currently have some kind of optimization which we will call as relaxed memory. This allows for certain kind of reorderings of instructions. So when I say most programs behave the same, a sequential program behaves exactly the same in the relaxed memory scenario, whereas the same cannot be said for the concurrent programs. These allow for very fast executions. For example, if you take a TSO, it allows for reads to overtake write. So the reads can be, the writes are cached or buffered. For each program, the writes are buffered and the reads can overtake this write. So it allows for a very fast execution when compared to the sequential consistency. We'll go into this TSO memory model in a bit more detail and not look at TSO and alpha for sake of the time. Now, what is TSO? TSO stands for total store order. Here, a read can overtake a write. What do I mean by read can overtake write? If there is a write instruction that is being performed by a program, the write might not necessarily go to the main memory, but a read can actually go to the main memory and read a value from main memory while the write is still in the buffer. So the writes are buffered in order. So write X and write Y of a program gets buffered as write X and write Y. So the order of the writes are maintained in the buffer, but they are buffered, they are cached in some sense. So what is a valid execution here? A valid execution is consistency under the relaxed program order. That is, there can be certain kind of reordering of instructions as permitted by the memory model, as permitted by the relaxed memory model, but the consistency with this relaxation has to be maintained. So here is one thing that I would like you to kind of think, that this allows for more behaviors than the sequential consistency. So if some execution is already sequentially consistent, then it is also total store order consistent. Whereas total store order allows for more relaxations in the sense that there can be certain kind of reorderings that can happen in total store order in what total store order allows, whereas the SC semantics does not allow. So let us take this total store order with the help of an example. So we have the same program, the mutual exclusion protocol here, and we'll see how it behaves in the total store order semantics. So what happens here? We have written the program or thread one actually writes a 1 to the to Y. This can be buffered now. So this is put into a buffered or cache, and it reads X from 0. Now the value in the main memory is still 0. So the thread 2 can write X to 1, write a 1 to X. This again goes to the buffer, and now both the main memory has X equal to 0 and Y equal to 0. Even though thread 1 already committed its Y equal to 1, committed as in it has performed this Y equal to 1. Now the second thread can read Y equal to 0, and in this case, uh, both the programs actually enter the critical section, and they can commit to memory much later. So, for example, both of them commit to memory much later. But unfortunately, in this case, the damage is done. Like both of them are in the critical section, which is not the intended behavior of the program. So, what does total store order? What is a valid execution in total store order? It is shuffle of the relaxed program. That is, I mean, you allow for the reordering of instructions within a thread, the allowed reorderings, and then ask for an execution with consistent reads. The other way of seeing it is there a consistent total order which encompasses the relaxed program order of the thread? So this is an example of total store order. There are multiple other memory models which we will not go into. So we already saw that there is a very unintended behavior of a concurrent program in total store order. I mean, we looked at a mutual exclusion protocol which failed in the total store order memory model. So it is important to check correctness for such concurrent programs in different relaxed memory scenarios or relaxed memory semantics. So one notion of correctness is reachability. The question is, given a concurrent program, given a configuration, and given a memory model, is there a valid execution according to this memory model which takes us to this configuration? So this can be used to check bad configuration. Suppose the given configuration is a bad configuration, then what you're asking for is a execution. It starts from the initial configuration, and you're asking whether the execution respects this memory model and takes you to the bad configuration. While this is very good, the reachability actually gives you a correctness guarantee. Unfortunately, the complexity is too high. For instance, even if you take a sequential consistent, the sequential consistency as your memory model, checking reachability can be piece-case complete. And if you ask for TSO or PSO, the complexity is even higher. For TSO, it is non-primitive recursive. So what you can do is now you can slightly reduce your or weaken your correctness criteria, and you can ask for consistency or testing consistency. This is what we call. The testing problem is, instead of asking whether there is a valid execution, we give executions of threads. That is, for each thread, we give an execution, individual executions. Now you are given a collection of these executions of thread. You are given a memory model, and you are given a concurrent program. Now you ask whether there is a valid execution involving these executions of thread. That is, let's say we have two threads, and you give an execution T1 and T2. Whether there is a shuffle of T1 and T2 such that it satisfies the axioms of the memory model and the reads are consistent. So this is what it asks. So such testing problem is useful to generate test cases. So you can extract out various executions of thread, and then you can check whether these lead you to a bad state, for instance. Unfortunately, this problem is also NP complete. So we will look at an example for this testing problem. Suppose P1, we have two threads, P1 and P2. P1 writes 1 to X, reads Y, reads a value of 1 in Y, and writes 1 to X again. And P2 does similar, except that X and Y's are interchanged. So it writes Y, 1, reads X, 1, and writes Y, 1 again. Now, what are the different valid executions involving these two executions of thread? That is the execution of P1 and the execution of P2. For example, this is a valid execution. Valid. So here, when I say valid, I'm assuming SC memory model. So this is a valid SC memory model consistent execution. So, I mean, P2 starts writing y comma 1, then P1 writes x comma 1, then P2 reads x comma 1, then P1 reads y comma 1. Notice that both x and 1 have value 1 in the memory. So the reads are consistent and the the execution continues. So there is also another execution for this which is valid. For example, this. We'll not go into this, but the idea here is there can be multiple executions which for a given set of executions there can be multiple valid executions that can be possible. So now what we do is so there are two sources of hardness. One is shuffling of the thread, and other one is where each of the reads take its values from. So what do I mean by where each of these reads take its values from? Let us look at it with the help of an example. It is the same example. Now, if you take this read of x comma 1 or read of y comma 1 in thread 2, this can read y comma 1 value from two different sources, either from the first write of y comma 1 or the second write of y comma 1. Similarly, read of x comma 1 can take values from two different sources. It can potentially take values from two different sources. So this is one source of hardness. The other source of hardness is how the threads themselves shuffle. Like in spite of fixing a particular read from value, the threads can shuffle in multiple ways. So these are the two sources of hardness for the NP completeness. So what we do in the rest of the talk is to eliminate one source of hardness, in the sense that we will assume a fixed read from relation. So what do I mean by this? So whatever I said now, we call it as data independence. So we will fix this read from relation in the given sequence of executions. So to make it more clear, this data independence can be seen as each writes an unique value. The write of y comma 2 does not repeat again. So every writes to a variable an unique value. So this is what we will assume for rest of the talk, and this is called data independence. So for example, in this thread, now since we have this data independence, we only have one write y comma 2, and if there is a read y comma 2, then it is you can uniquely determine from which write this read happened. So this is what we will assume. So now the testing problem is redefined as, given a data independent execution of threads, that is, you are given a collection of one execution per thread, and each of them, this collection is guaranteed to be data independent. You are also given a memory model. Now the question is there a valid execution for this memory model involving the given set of threads? So this is the problem that we are interested in. This is the testing problem that we are interested in. So one thing about this data independent assumption is this is not introduced. It is not introduced by us, but it has been well studied both in this context and also in the other contexts. Unfortunately, the problem is still NP complete. As I had already said, there are two sources of hardness for this NP completeness. Even if you eliminate this read from hardness, you still have the hardness that comes from the shuffling of the threads. So the problem is still NP complete. So what? Yeah, we'll now look at an optimal framework. What do I mean by optimal framework? We look at this problem from the FPT perspective. FPT stands for fixed parameter tractability. Now, in addition to the input already we saw, we are also given a parameter. k, which is the number of writes in our case. Now we ask whether there is an algorithm for testing consistency which runs polynomial in the size of input, maybe exponential in the parameter. So a problem is said to be fixed parameter tractable if there is a if there is an algorithm which runs only polynomial in the size of the input and and arbitrary in the size of parameter. Now there is a simple algorithm for this. Simple as in there's already a way to check consistency given a total ordering of writes, whether this particular total ordering allows a consistent execution. Based on this already known algorithm, we can obtain a simple FPT algorithm by iterating over all the total orders of writes. The complexity for this will be O star of k power k. Here O star ignores or masks the polynomial running time of the algorithm. A natural question here to ask would be whether this is an optimal algorithm. Apparently not. So we, in our paper, provide an improved algorithm based on dynamic programming. The improved algorithm operates on subset of writes as opposed to the total ordering. So how do we do this? Given a set of writes, say V, we check whether there is a consistent total order involving this set of writes. How do we do this? So let V be the set of writes. So we take an element out of it. We consider a small v from this capital V, and then we also consider the rest of the elements of V. Now we decompose V as the small v and V dash, and then we ask whether there is a consistent total ordering involving V dash, and with V as the minimal element and V dash as something that comes after it in the total order, is there a consistent execution? So I would like to stress upon the fact that here we have lost the total ordering involving V dash. So we are checking for consistency with V as the minimal element and V dash as a set. So we do not have the total ordering involving V dash. So this is slightly non-trivial, and details can be found in our paper. So using this method, we get a recurrence relation, and this recurrence relation can be used to obtain a improved algorithm which runs in O star of 2 power k. Then instantiating this on SC, TSO, and PSO, we can get algorithms for these memory models with running time of 2 power k. We also show optimality assuming ETH. What does ETH say? ETH says that 3 SAT with n variables and m classes cannot be solved in time, 2 power small o of n plus m. And we show how to construct from a given 3 SAT instance, SC, TSO, or PSO with at most n plus m writes. That is, given a 3 SAT instance, we construct an SC instance with n plus m writes, Similarly, given a 3 SAT instance, we can construct a TSO instance with n plus m writes, and so on. So with this, we also show that each of these problems, SC, TSO, and PSO, there cannot be a running algorithm with running time better than 2 power small o of k. Yeah, thank you.